The second fundamental theorem of calculus is very easy to actually perform the operations. It's a little bit different, a little bit of a different story when it comes to actually understanding why it works the way it does. All right, so what we're dealing with is an accumulation function. Well, it says it right there, but it's a function that represents the accumulation of area over an interval. All right, so it's kind of a weird thing to think about, but basically we're creating a function from another function, right? So you look at this and it very much looks like a typo, but it's not. We have the antiderivative over the interval of a to x of f of t dt, all right? So f of t dt is a function of t. We're integrating that, but then we're integrating it over an interval of a to some unknown upper bound, all right? That unknown upper bound is the function x, all right? So we're allowing this to accumulate over a variable interval, all right? So that variable interval allows us to create a new function with a new variable from the original function, all right? So that's weird, but let's think about this in notation form, because you see this bad boy right here, and you see the derivative with respect to x of this integral is somehow equal to f of x. So let's actually play that out real quick. I'll just do it kind of off on the side here. So let's say I wanted to integrate f of t dt over the interval of a to x. Okay. What would be the antiderivative of lowercase f of t? There's a reason why I said it that way. Uppercase, capital F of t. On the interval of a to x. All right. So in understanding the second fundamental theorem of calculus, I'm actually going to apply the first fundamental theorem of calculus, which is to say I anti-differentiate and I plug my bounds in and subtract. So capital F of x minus capital F of a. All right. So that's what our integral would be equal to. Now, what I want to do is take the derivative of this with respect to x. All right. So I'm going to slap a d dx on the front of this. Just slap it right on. Yep. What that's asking me to do is differentiate each part, all right? So what would be the derivative of capital F of x? Lowercase f of x. And what would be the derivative with respect to x of capital F of a? 0.
It's a constant.
It's a constant. Yep. Right, that's the little trick to it, because you want to say lowercase f of a, but then that would put you in a spot where you're like, well, we didn't get f of x. Now, even if you didn't know that, you probably would have figured it had to go to 0 just because the rule tells us it's going to go to f of x, but it is because it's a constant that this differentiates down to 0. All right? So that's actually the proof behind the second fundamental theorem of calculus. But it's actually pretty cool because really, if you think about it, I'll just throw a quick side example here. Let's say I have f of t is equal to e to the t. Keep it relatively simple. All right. If the question asked me to find the derivative with respect to x on the interval of, let's say, 2 to x of that function f of t. So I'll just write the e to the t in there. dt. That's just going to give us e to the x as a result. All right, because we left the lower bound of integration variable, that means that it really didn't matter what a was. That part of it was always going to zero out. Because f of a, f of 2, f of 20, f of pi, still going to be constant. When you differentiate it, it's going to go to 0. All right? So in this case, I wanted my lower bound to be equal to 2. All right, so that's cool. It's still going to go to 0. Right? So my rule allows me to just take whatever the inner function is and replace the variable with the upper bound of integration. But there's a little bit more to it than that. Of course there is. Because why wouldn't there be? Let's say you have a question where they ask you to find the derivative with respect to x on the interval of 3 to the sine of x of e to the t dt. All right. So there's a hidden step in this process. All right. The hidden step is that we are applying the chain rule when we're taking the derivative. So we're just not showing the work. It's just kind of a little bit of a shortcut. But if I were to take the derivative of capital F of x, if x were some more elaborate function, so the inner function was more complicated, you'd have to multiply by its derivative, all right? You'd have to apply the chain rule, all right? Because the upper bound of integration was just x, the inner function was just x, the derivative of x is equal to 1. But here, it wouldn't be f of x, in this situation, it'd be f of sine of x, all right? So we have that little extra component there, all right? So what we'd be looking at would be e to the sine of x. But again, because there's an inner function, I have to multiply by something. What would that something be? Cosine x. All right. All right. Just because, again, there's a hidden step here. We were multiplying by 1. We just didn't have to show the work. Here, we do have to show what that multiplier would be. All right. So this is like the first step in a process that doesn't really pay itself off until Calc 3, which kind of stinks. It's yet another one of those topics. And in fact, I don't even know if I picked up on it when I was a student taking Calc 3. Like, I didn't pick up on the payoff. I picked up on it when I started teaching Calc 3. And I was like, oh, that's where Fundamental Theorem Part 2 comes into play. Wow. That's like Red Skull.
Bruh.
It's crazy.
Yeah.
What does that mean?
That was an Infinity War.
Well, it was both. It was a both.
Well, I was trying to.
Will.
Oh.
Did it again.
You always do that. What's wrong with you? Hey, this is the first.
That's why I paused, because I was trying to go through my mind for nothing spoilery. Yeah, Red Skull and Captain America, Red Skull and Infinity
Who
War.
hasn't seen it? Oh.
Just
We only
Nobody
watched
speak.
class. Wow. How have you not
Oh,
seen
is Captain America that original movie
I mean-
from that character?
It's just like,
Captain
you haven't
America,
seen it
the
at
first
this point.
Avenger.
Like, how can you not?
Yeah.
It's been a
I haven't seen anything before Infinity War, so I don't know where that works.
Oh,
No, I'm being
No.
yeah, that's
My point is,
a lot of unexplained phenomena. Like, for example, when Rocket wants the Winter Soldier's metal arm, that means nothing
I
to
will.
you.
Yeah.
Gotcha.
Really?
And when he gave Thor the eyeball, that also means
Yeah,
nothing to
that
you,
was-
except the part where he, made a joke out of how he got it off of
Yeah.
the planet. But that was funny for everyone, and disgusting.
Stop.
So
That was probably the most referenceable time.
anyway, this example here, the one that I didn't even bother doing,
Sorry.
is really just kind of building up to the idea that the antiderivative over an interval gives us a function. All right, so if they're telling us that capital F of x is equal to the integral of cosine over the interval of 0 to x, what I can do is I can actually perform that integration. All right, so we know that the antiderivative of cosine is what? Sine over the interval of 0 to x. Oh, I wrote x. Meh. Well, I kind of jumped the gun. So ultimately, it'll end up being the sine of x. All right, so it's not overly meaningful, at least contextually at this point, because we don't know what, well, I mean, we could assume that t probably means time and x means distance, but what we're doing, like, and if you operate under that assumption, is what we're doing is creating a relationship between distance and time, right? Horizontal distance and time. And so that allows us to do it, to perform a change of variables. So if you think in terms of parametric equations, so that basketball project that we did way back when, the idea is that there is a relationship between time and distance, provided you know kind of what that relationship is. And usually that comes through experimentation. Here it's coming through the act of integrating, right? So it establishes a relationship which allows you to convert from one variable to another. Right? So that's really just the gist of it. There's a lot more to it than that, but that's the general sense of it. And then from this function, I can evaluate, I can find f of 0, which would be 0. According to the diagram, that makes sense. No area has been accumulated. How much area would have been accumulated after I've gone pi over 6 in the x direction? Sine of pi over 6, which is 1/2. All right. Sine of pi over 4, root 2 over 2. Sine of pi over 3, root 3 over 2. And sine of pi over 2, which would be 1. All right, so what we get from this, because again, the original function was defined in terms of time. So what we're saying is that a particle, for example, follows a model of y equals the cosine of t, where t is measured in seconds. All right, on the interval of 0 to pi over 2 seconds, how far has it traveled? And so you would say, okay, well, I could just integrate. But then you would think, well, we're talking about a distance here, right? So I would be thinking in terms of the accumulation of distance. So would I necessarily want to be working in units of time, right? So I can relate time with a y value, or I can relate x with a y value. So you think position versus so position in terms of x and y, or a parameterized position in terms of time and x. All right, so it's a different way of thinking about it. All right, so I kind of equate it to the roller coaster analogy, which is to say that if I were to create a graph of a roller coaster, there's a couple of ways I can do it. One way would be to actually create the path of the roller coaster, right, which would be x against y. The other way another way would be to create a graph of time against height, in which case, as time increases, I would still have kind of like maybe a sinusoidal, it could be polynomial or whatever, but the idea would be that the heights would change as time increased, right? But it's only representing height, right? Kind of like those parabola problems you did back in Algebra 2, where it was time versus height. But it always looked like it was just a parabola. But it somehow represented just a ball being dropped from the top of the Empire State Building, for example. Right? The ball didn't follow a path that was parabolic, but time against height is represented or modeled in a parabolic fashion. All right? So it's a different way of thinking. And this kind of lends itself to that. And you're not just limited to linear distances versus time. We can convert from arc lengths to linear distances. We can relate time to arc lengths. We can do a lot of different things. So we can branch this out into circular math, which gets us into the third dimension, which was the Calc 3 reference that I made earlier. All right.